Hello, my freshmen. Sorry I can't be there with you today. I have a meeting in the district that I have to attend. But today we need to finish up some stuff and kind of wrap some things up that we've been working on the last couple days. First of all, open your lab notebooks up to your drawing force diagram notes. That would have been right before the Newton's first law activities that we did last week. So I'll give you a minute or two to go ahead and find that. All right, so now everybody's opened their lab notebook up to drawing force diagrams notes. I believe we had gotten to the point right about here where we were starting to draw in the forces acting on the chair. Okay, so let's get rolling on this. So when we're on Earth, one of the first things I always like to draw is I start on the object and I pull with an arrow going down. And I label that, hey, that's the Earth, F sub Earth, pulling down. Now I always label the force with the object causing the force. So it's the Earth pulling it down, not just the core of the Earth, but the entire Earth pulling straight down on it. Then I have to ask myself, well, why doesn't this chair fall if the Earth is pulling it down? Well, that's because the ground, or the floor, is pushing it up. So this is the force of the floor. Heck, in this case, if I wanted to, I could call this Earth as well, because ultimately it's the Earth that's doing this force. So we have an upwards force, a downward force. Well, this is a picture of somebody pushing the chair. So there'll be somebody standing right here, and they'll be pushing the chair this way. And I say, hey, that's the force of the person pushing the chair. All right, so whoever person that is. If you want to instead, if you want to instead use a name like Bill or Lisa or something else here, you could do that as well. And then there's one more force that might be hard to see right away. But whenever an object grinds along another object or rolls another object, there's going to be a frictional force. The only problem with that, so that frictional force is going to point against the way we're moving. So friction doesn't ever push you with you, it always pushes against you. So, whoops, sorry. So I'm going to just draw a force back here. And the length of these arrows right now doesn't matter. The only thing we're focused on right now is getting the object right and getting the direction right. The size doesn't make a big difference right now. So in this case, I'm going to call this F, but then I figure out what's causing that force. And the object that causes that force is the ground as well. So it's the floor. It's friction with the floor that causes it. So the force of the floor is pushing back this way, and this is a frictional force, right? Right here, this last one. Awesome. So our simple little chair pushed across the thing have 4 forces acting on it. It's actually a really complex system that looks really simple at first. So if you still need more time, say something and we'll pause the video. Otherwise, we're going to move forward. So let's do a few more examples. I want you to draw all these examples in your notes. Let's talk about a baseball flying up. Well, we're talking about a baseball. We're probably on Earth. Pretty safe to bet that we're on Earth. So we're going to draw that first easy one. I'm going to grab the ball right here, and I'm going to pull down. I'm going to call that F of the Earth, pulling down. Awesome. So now I have to ask myself, so it's flying up, so it's going in this direction like this, right? So I have to ask myself, well, what pushes it in that direction? And I think right away, I'm like, okay, so there's a force here, and that force is from what object? We say, okay, it's the force of the hand, right? The problem is there is no hand pushing on it right now. The hand did push on it way over here, but there isn't a hand pushing on it right now. So it can't be hand. All right, so let's erase the word hand and figure out what force is pushing it. So then what could be causing this? Yeah, maybe it's the baseball, or maybe it's the inertia or the mass of the ball pushing it forward. And if that's true, that means that an object can push itself forward, which means when you're on a skateboard, if you just grab your shirt and pull forward, you can pull yourself forward? No. So the hard conclusion to come to is that there isn't a force in the forward direction here. And we actually know that's true. We already know that an object in motion will just stay in motion. It doesn't have to be pushed. This baseball will just stay in motion going in a straight line unless something makes it speed up, slow down, or turn. In this case, the force of the earth here is going to make the baseball turn and not go in a straight line forever and ever. All right, now there is one more force. Whenever we're moving through air, we have a resistance. The air resists us, and it's a frictional force, and it's going to push against our motion. So if we're moving this way, the air force is going to push this way. I think it's a fairly small force, so I put it as a small arrow. Again, today we're not worried about the size of the arrows, just the direction and the objects causing them. And in this case, the air is causing that force. Force of the air pushing back on the ball, and the force of the earth. Those are the only two forces. So this baseball should fall and slow down. And that's what we see when we throw a baseball, is that it gets slow over time and then it falls down to the ground. Awesome. And then now let's go with the coming back down. So let me erase these real quick. Awesome. And again, we're on Earth, so first easy force, F of Earth. And then there is no forward force here. Again, there's nothing pushing it forward. Objects in motion just stay in motion. The reason it's curving and doing different things is because of this force of the earth here. And it's moving in this direction. The air is going to push against it in this direction. That is the force of the air. And again, I chose to make that small, but it doesn't matter how big you make it right now, as long as you get the direction correct against the direction of the ball and the right object. Awesome. So you can tell coming up or going up and coming back down are very similar force diagrams. The only thing that changes is the direction of this air force and possibly the size of it. All right. Now let's do the race car. So again, we're very likely on Earth. So I'm going to grab the car. I'm going to say, okay, so the Earth pulls the car down. And I have to ask myself, well, why doesn't the car fall? Well, that's because the road is pushing up on the car. F of the road. Now here I could label this earth or ground or road or anything like that. Is totally fine as long as you get an appropriate thing. I wouldn't want to say the tires push the car up, because if I took the ground away, the tires wouldn't keep the car up. It would totally fall. It really does need the ground or the road here in order to push it up. So I have those two forces that I've gotten taken care of. Now, if this car is moving, there's going to be some backwards force. We're moving through the air. There's going to be some backwards force of the air pushing back on the car. And if you're like, what? Come on, that's not a big deal. If you go at 55 miles an hour, stick your hand out the window, you'll think, oh, wait, yeah, that's a pretty big force, especially when it's pushing on the entire front of the car. If you imagine, instead of sticking your hand out the window, stick out like a sheet of plywood that's the same size as the front of your car, and it would be like, rah, rip your arms off. So this force of air backwards is really significant. And then so the question is then, what pushes the car forward? Now we know there's got to be a forward force here, because we have to, act against this air force. So it's like, well, what pushes it forward? Do the tires push it forward? Does the engine push the car forward? And you might say, yeah, those things are true. But here's the problem. If I drop a car out of an airplane and hit the gas, I don't just start driving forward. I just keep falling straight down. I won't actually drive forward till the wheels hit the ground. So it's not really the wheels doing the pushing, it's the ground doing the pushing, because the wheels push the ground backwards, the ground pushes you forward, just like the walking. And that's why we did Newton's third law first, so we can understand this better. So this is actually the force of the ground, or I should say the force of the road even. You could say ground if you wanted to. This is the force of the road pushing you forward. Without the road, you don't go forward. So again, 4 forces. Awesome. There goes the car. And let me erase these things really quickly. And we've got one more to do. Oh, helicopter. This one's super fun. All right. So, again, I'm assuming that we're talking about Earth, because it would be weird to have a helicopter not on Earth. So we have the Earth pulling down. And then, so what keeps the helicopter from falling? Well, it's not touching the ground. It's up in the air. The blades of the propeller are moving, and the blades push air down, which Newton's third law tells us if the propeller pushes air down, the air pushes the propeller up. So we have an upwards force on the propellers here. And we need to label that F, and then what object causes that force? Oh gosh, it's surprising, but it's the air that's being pushed down, pushes it up. So that's it for the helicopter. We've got air pushing up, Earth pulling down. There's no object pushing it forward or backwards. We're all good. All right, again, so what I want you to do now is work on pages, I think it's 6 and 7, but it's the force diagram pages in your homework packet. And we'll give you about 15-20 minutes to do that. And practice getting the direction of the forces right and the object right. And you can work it as a little poll as you go through this as well, helping each other figure it out. So the object here isn't to race through as fast as you can, but to make sure everybody at your table understands what's happening and can kind of work through these force diagrams. So go ahead and pause the video now and work on that. All right, so now we're back from doing the force diagrams. If you didn't finish those up, be sure to finish those up for homework tonight. We'll check them first thing tomorrow in class. So Newton's first law on Earth. These notes are with the Newton's first law notes. I believe the place we left off actually was right here. So an object at rest will remain at rest, an object in motion will remain in motion, traveling a straight line at constant speed, unless acted on by an unbalanced outside force. So this is our Newton's first law statement. We went through Newton's first law stations to practice using this statement and understanding what it means. Today we need to pick up where we left off here and those notes and understand Newton's first law on Earth, because we've never had this experience of throwing an object and it staying in motion forever. And the question is, why not? Because Newton's first law says that things in motion should just stay in motion. So why do things slow down and stop on Earth? Well, the first intuition that people have is to say, oh, well, because gravity slows things down. But you need to be careful, because if gravity slowed things down, the Earth has been rotating around the sun for billions of years now. And if gravity slowed it down, the force of gravity from the sun, or the force of the sun, would have slowed the Earth down and stopped it long, long time ago. So it's actually not gravity that slows things down. What does slow things down is when gravity, or when the force of the Earth pulls an object down to the Earth, and then the object grinds against the Earth and stops. It's friction that slows things down. The only thing that the force of the Earth, or the gravitational force, does is it just brings two objects together so they can grind together and stop. But it's friction that makes things stop, and that is the key role, or that's the key force that stops things. So it's that grinding between the two objects that slows things down and stops them, or pushing through the air will slow you down as well. But it's definitely not gravity. We want to make sure that's clear. So in space, since there's no gravity to pull objects, I shouldn't say that. So since the gravitational force is so weak in space between two objects, they tend to just glide by each other and not grind and rub together. So the only reason that there's little to no friction in space is because there's little to no grinding and rubbing in space, because objects aren't being pulled down together strongly. So that means in space that objects will travel in a straight line at constant velocity unless acted on by an outside force, like the force of gravity from some planet or running into something. Other than that, though, straight line forever and ever and ever. They won't speed up or slow down. They won't run out of speed or slow down or anything. And this was a way cool idea. I mean, it would have been hard to be the first human to kind of come up with this and go, how am I going to explain this to people that everything they've ever seen has to be rethought? And that was Newton's role. It was a fantastic, cool role. All right, so that's it for the notes for today. I hope things went well. And if you didn't finish up your homework tonight is to do the Newton's first law pages, which are the 2 pages right after the drawings, the force diagram drawings. Have those ready for tomorrow, as well as the force diagram drawings. So it's a lot for homework tonight. Make sure they're ready to go. We'll stamp both tomorrow in class, and we will check them both. Cool beans. Have a great one, my friends. We'll see you Tuesday.